welcome to lecture 13. So today we'll quickly look at commands, but what I will do is I'll look at a commands in a sort of simplified setting. So we have previously looked at expressions and declarations, which are two important classes of syntactical categories with different meanings. However, I don't want to complicate matters by introducing commands on them. Instead, I'll introduce commands separately with expressions, and then later we'll integrate them with declarations. So for the purposes of this lecture, we'll just assume a while language, which is like the most skeletally complete language for programming, structured language for programming, if you like. So what we'll assume is that we have a language with no declarations, but you can have lots of identifiers, and all those identifiers are variables in the imperative programming sense, in the sense just like in Pascal or some such thing. So, and of course for the present, while we are still discussing the various major syntactic categories, we'll assume that our variables are only integer variables, right? So there are no declarations, but we'll assume that we can freely update variables. So we have, and since there are no declarations, we really cannot, without a declaration, we really cannot distinguish between a constant and a variable. So we'll assume that there are no constants. Later, when we integrate declarations into this imperative language, then we'll also look at environments and so on and so forth. So for the present, we'll just assume that we have got this simple imperative language, which consists of a language of expressions, which have literals, integer variables, and the standard operations, let's say the binary operations on integers. Right, and of course, since we are going to, a program in this language is just a command. I've written it in a bottom-up fashion, but really the commands form a complete program is just a command. Okay, and since we have conditions here, we require a sublanguage of Boolean expressions also. So I'll assume a simplified sublanguage of Boolean expressions, right? And since there are no declarations, I don't want to complicate matters by allowing Boolean variables. I'll just assume that there is a Boolean constant in the language called true, and the only kind of Boolean expression which consists of integer expressions is an equality checking expression. So, and otherwise you can have negation or disjunction. I just chose OR because, well, you have to choose one binary operator. The rest is simple. One unary operator, one binary operator, and one constant. Besides this equality of expressions, and our main grammatical category is that of a command. Is that of a command, whose basis, of course, is an assignment statement. There is a sequential composition of commands, as in a language like Pascal, and there are these conditional commands and looping command, right? So in the last week, in the last few lectures, we looked at an expression language with declarations. So it was very much like a functional language. Here we are looking mainly at an imperative language without declarations, because in an imperative language the main syntactic category are commands. Right? So let's look at this. So if we have to give a semantics of this simplified language, we should, in some sense, we should be faithful to the previous operational semantics that we have already given for expressions, except that now, since we are considering an imperative language with an assignment statement, there is an updation of variables, and so we have to come up with a suitable concept which allows for updation of variables. So, and of course there are those usual criteria like we should not unnecessarily load our semantics with pragmatic features. We should not unnecessarily bring in data structures or algorithms. We should just give minimal, concise rules which will specify the language in machine independent, architecture independent fashion, right. So what we'll do, and something that you must have all seen in your programming courses, is the concept of a state. In fact, that's in fact the most common way of describing imperative languages, that they are state based languages, right. So there is a concept of state which is some abstract entity, and for our purposes and for the purposes of most discussions on the pros and cons of imperative versus functional languages, a state is really nothing more than a variable value binding. In that sense, it looks no different than what we said about declarations in the functional language. They were also just identifier value bindings. Okay. So, however, here the difference, the reason a state is different from an environment for our purposes is that this variable value binding is really represents bindings that can change with time, right, as we will see the thing, as we will see in the semantics. Okay. So the semantics of this while language is important because practically everything that you want, if you want to talk about a simplified imperative programming language, everybody would pick up a while language and give it essentially just a state based semantics, or define its meaning in a state based manner. In all programming courses also the while language is considered the basic building block through which programming is taught, and you talk about states and you talk about changes in state and so on and so forth. So it's instructive to look at it. At the same time, by looking at it in this simplified fashion, we might also understand how to express the semantics of Boolean expressions and in general what happens in the case of commands, right. So we'll combine all these things in a single framework, and then we'll go on to actually looking at programming languages in which this notion of state is not sufficient, and you require to augment it with a different concept, right, which is closely related to it and closely related to environments, but is actually separate, right. So we'll just assume that expressions are evaluated in a state. This is a very simplistic assumption, and commands are state transformers. And that's really what happens in the case of an imperative language. Each command can modify the state in some fashion. And those state changes, the state transformations, are irreversible changes. Yeah, in the sense that to undo the change requires at least as much effort as was required to make the change, right. So we'll look at just state as an abstract concept which has got nothing to do with val memory or whatever, and we'll look at state changes. So given two states sigma and sigma prime belonging to the set of states, we assume that there is a predefined collection of variables V always. Since there are no declarations, we have to assume an unbounded collection of variables available to us, and we'll just assume that they all have some value associated with them. Very often that value could be undefined. So you could augment your value domain with some element called the undefined, and you could initially, an uninitialized variable could be regarded as something that is got the value undefined, right? These things of course have representations in actual hardware. I mean, there is a null value which can be used, which is not a data value belonging to any type, right? So so I will consider the change from sigma to sigma prime as, and represented in this fashion, as a one point change, in the sense that sigma and sigma prime are everywhere identical except at the variable I, okay, and at the variable I, whatever sigma might be, whatever may be the image of I in the state sigma, in the state sigma prime its value is n, and that's what this indicates, right? So what we are saying is that sigma prime is everywhere identical to sigma except at I, where sigma prime has the value n, and what sigma has is of no concern, or it has some value but it may not be the same as n, yeah. And for all that means, so what it means is for all other variables, for all variables other than I, sigma and sigma prime yield the same value, and for I, sigma prime yields the value n, right? So this is a very important thing, because the assignment statement involves a one point state change, right? So it's absolutely basic. So we'll go through this semantics of this language in a sort of rapid fire fashion, so that it acts as a revision of whatever we have previously done and introduces a few new concepts at the same time, right? So the language of expressions, well, it's not very different from whatever we have previously defined. It's just that now we are looking at expressions evaluated in a state. So you can think of it as replacing rho by sigma, if you like. But but to be more rigorous, what we'll do is we'll look upon the evaluation. We'll look upon the set of configurations for expressions. So everywhere you carry a state with you in the execution of a program, and the set of configurations of expressions is just the collection of all ordered pairs of expressions and states, right? And the set of terminal configurations is just the collection of numerals along with the state, right? And so we have to define the transition function. So I have put a prime everywhere to distinguish it from the last semantics, but you will see that it doesn't look too different from the last semantics, right? So let's quickly go through the expression language, and you will see that it is more or less like the last one, except that since I am considering expressions to be ordered pairs of this form, the meaning of an expression I in the state sigma is the value assigned by sigma to I in the state sigma, right? So it's just the value of the expression I in the state sigma, and of course you carry the state along with you every time. The meaning of an operation, a binary operation on two constants, on two literals, is really whatever assuming that that binary operation is already available in the underlying virtual machine is just whatever is the result provided by that operation in the underlying virtual machine, right. This is the base case of left to right evaluation for expressions. So this rule just says that given a constant m, binary operations, some expression E, this goes to m binary operation E prime, provided in the state sigma the expression E can move to E prime in the same state sigma. Note that we are considering a very simplified language in which there are no state changes that occur in the evaluation of expressions, right. Then going further, given a complicated expression of the form E1 binary operation E2 in a state sigma, our left to right evaluation strategy says that in this state sigma, if E1 moves to E1 prime, then this binary this complicated expression moves to this complicated expression in the same state, right. So the rules E naught to E prime naught to E prime 3 are really a sort of a syntactic translation of the rules we gave E naught to E3 for left to right evaluation of expressions under some environment, right. So now of course since it's an imperative language with conditional statements and looping statements, what it also means is that we have a separate categories of Boolean expressions. So in addition to before we can actually give the semantics of the commands, we have to define the semantics of Boolean expressions. So let's quickly look at the semantics of Boolean expressions. So I'll assume that the set of Boolean expressions that are possible includes all Boolean expressions that we already have and two predefined constants t and f denoting true and false. There is no reason why we should assume that t and f have a representation similar to that of the constants there. I mean, they could be, we could be type respecting in whatever we do, and we might keep Boolean constants separate from let's say integer constants. And this is not too outlandish. This is not too outlandish because there are architectures, for example, which are tagged. So in many tagged architectures, there is a tag associated with every memory location in which a type could be specified, and storage is allocated only based on the type, right. So this is not too obscure or outlandish, and we'll as we did in the case of the declaration language, though I have not explicitly specified it here, we will also include these constants t and f as part of the Boolean expression language, right. So in addition to so you can think of the Boolean expressions as having in addition an extra production of this form two productions of this form, and the language that we will be considering for semantic purposes includes these two. So you can form Boolean expressions with these constants and so on and so forth. In the process of evaluating a Boolean expression, you will also include these constants, yeah, as part of the semantic. No. That this true is a language specific syntactic entity. This t is a constant available in the underlying virtual machine. Okay, the two are not the same. I mean, they are not exactly the same. If you want to make them the same, that's a different matter. But this true is well, it's in the syntax of the language, and you'll always be using this. You'll never in a program actually use this T or this F. Right? This T or this F is some constant provided in the underlying virtual machine. Anyway, anyway, let's not nitpick too much, because what will happen is that the semantics of this true will just turn out to be this T. I mean, that's it in a single step. I mean, there's nothing more to it. Okay, so it's not a serious it's not a very serious matter. If you want, you could, for example, have gotten rid of this true and put this T and F here, just as much as having it separate, right? But very often you have to distinguish between an element of a language from an element of its meaning. This is something that should be clear from whatever you've done on, for example, all of you have studied truth tables, right? So if you look upon Boolean expressions as a language, then there is a separate construct called true and a separate construct called false. In this truth table semantics, what you actually give are not the constructs of the language, but of a semantic domain which consists of two different values, in which the true and the false have corresponding representations. Right? I mean, if you've been mixing up these two, I mean, that's it's not a serious matter, but the distinction between syntax and semantics has to be kept clear. I mean, one of the things that you do is you actually if you can define the language of, let's say, I don't know, propositional logic or Boolean expressions without the syntactic constants true and false. I may not have it at all. After all, why should I? I could just have propositional variables, no true and no false. If I want a representation of true or false, I'll take it to be of the form A or not A. There is absolutely no need to introduce true into this syntactic language. Right? I mean, I could keep true and false purely in the semantic language and have a language of Boolean expressions which is totally expressive. It's not as if the constants true and false cannot be expressed. I could just have the various operators. I mean, I could have, let's say, various Boolean constants other than true and false. For example, I could just define the language of Boolean expressions, or let's assume that you have truth values, right? So I could just define it to be a language which consists of a set of Boolean variables, right? And just these operations, not A or A, A and A. There is nothing which tells me that I should have true and false in the language at all. Right? So I can define a complete propositional set. I mean, this is a complete set of adequate connectives for propositional logic or for Boolean algebra. I don't need to have the constants true or false.
What is X?
X is just an identifier or a propositional variable or a propositional constant, a Boolean variable or a Boolean constant, other than true or false. Yeah, it's just okay. Now this is a completely adequate set of connectives for Boolean algebra. What I might do is, in specifying the semantics of this through truth tables, what I might specify is that my semantic function is a truth value function which maps the set of all I don't know, the set of all the set of all propositions. So let me call this the language of propositions. It just maps this to the collection of truth values T and F. Right, and I'll give, and what the important thing to realize is that whatever is in green is the language of propositional logic. Whatever I specify in the truth table is really a function of the function called T, which maps, given a truth value assignment to each of these identifiers, it gives me a truth value of compound expressions, and there is no true anywhere in the language. Right? I mean, this should be this is not been made explicit in any of your previous courses, but essentially it's that there is a semantic domain called T and F, which is completely different from the language of Boolean expressions or from the language of propositional logic. Right? So the fact that I've introduced true in the language is just it's just something I just did. I wanted to introduce a Boolean constant, so I introduced it. But this, it's enough for me to have these three connectives, and I can get all possible propositions that I want. Yeah. So this T and F belong to the underlying semantic domain. They do not belong. They need not belong to the language, to the syntax of the language at all. It's a different matter that very often you introduce because you want to specify that for example, a tautology is an identity for the AND operation, or a contradiction is an identity for the OR operation. So what you do is you explicitly introduce two separate constants, let's say true and false, to make it distinguish from T and F into your language, so that you can specify those equations in a convenient fashion. But there's absolutely no reason why you should do that. I could specify a tautology as of the form A or not A. I could specify a contradiction of the form A and not A. Yeah. So that the fact that I have introduced a constant into the language is really just my business. The constant may not be in the language at all. It's part of, this thing is part of the language. What is there in the underlying semantic domain are these truth values. Yeah. So let's look at so what I'm saying is that this is not necessarily the same as this, and your elementary knowledge of architecture or whatever or hardware will tell you that there is an explicit true in Pascal, but what is its actual representation in the hardware is not true at all. I mean, it's something else, I mean, depending on the underlying representation. Yeah. Right. So okay. Right. So let's look at the semantics of Boolean expressions. So we have this set B along with these two constants T and F, and we have a set of configurations which I'll call gamma B, which is just this entire set. Actually it should be this B includes this T and F too. Okay. Unless it includes this T and F, you cannot have a set of terminal configurations of this form, right? So you might as well introduce this as equal to some b prime if you like, and call this b prime instead, right? So so you have this set of final configurations, and my first rule for the semantics of Boolean expressions is just that the constant true evaluated in any state sigma gives me this, the t of the underlying, the truth value of the underlying machine or interpretation, right? And a knot of this constant t is f. This knot is again an entity, an operator of the language, and it's got nothing to do with anything that might be there in the hardware, right? Okay, if you got a unary operator, so then this is the basis of the NOT operation, and this is the induction step if you like. So if you have a complicated Boolean expression b which is being negated with a NOT, then you can evaluate this NOT only after you have evaluated b and brought it down to a truth value, right? So if b is some complicated Boolean expression, it might have to be evaluated in several steps, in which case it might, remember that they are all syntactic transformations, so symbol manipulations. This b might go to some b prime, and therefore this not b will go to not b prime, and this rule will be applied several times till finally this b has been reduced to a truth value. Okay, there should be one more rule which says not f sigma is t sigma 2, right? So let me introduce that. So there is a b1 prime which I will introduce here. Right, so this is not f is equal to t, right? So, and that gives me a complete set of evaluations of Boolean expressions, except that our Boolean expression language really depends upon that's for the NOT operation. So we have to look at the OR operation. So here is the semantics of the OR operation. Again, as in the case of the expression language, we will look at left to right evaluations, right? So if you have got a complicated expression of the form b1 or b2, then you first evaluate b1 till you reduce it to a truth value. Then you evaluate b2 till you again reduce it to a truth value, and once you've got two pure truth values, you can actually get another truth value, and of course this b5 should actually be, b4 should actually be replicated separately for t and separately for f. Similarly, b5 will actually have 4 copies depending upon this truth table, right? So I've used this question mark, inverted question mark and exclamation as being elements of this semantic domain, arbitrary elements, and the connections between them are given by the truth table, right? So actually there are like four different versions of b5 depending upon the truth values that you're interested in, and similarly several versions of b4, one for each truth value. But I don't want to stress it too much, because these are elementary materials. So yeah. So rather than use new variables and so on and so forth, I have used these symbols as variables over the semantic domain. Yeah. Okay. So this is as far as Boolean expressions are concerned and combinations of Boolean expressions are concerned, except that our Boolean expressions, the only way we can form Boolean expressions are through equality of expressions, right. So we have to look at expression equality, so which means the evaluation of equality is again specified in some such fashion. It has to be related to the transition system for the expressions, and B6 and B7, just as they did for the expression language, for binary operators in an expression language, they do the same for the equality, where equality is really regarded as a binary Boolean operation between expressions, right. So this B6 and B7 again specify B6, B7 and B8 actually specify a left to right evaluation of expressions to yield an appropriate truth value, where it must be understood that the resulting truth value says that these two constants, I have used 3 lines here to indicate that we are not talking about just equality of constants, but they should be identical as patterns. They should be identical as patterns, and that's the only way a machine with no intelligence can really recognize equality. Given that it has no other information, what it can recognize as equality are just 2 identical patterns, right. So if the 2 patterns that you get from evaluating E1 and E2 are identical, though I have given them different names here, then you would say that this yields a true, otherwise it yields a false, right. Now there's one thing about this. In our grammar we actually specified the Boolean expressions as a separate grammatical category which used the expression language, and whereas here we are treating Boolean expressions, the equality of Boolean expressions, at essentially the same level as the expression language. We are specifying a left to right evaluation of an equality expression and so on and so forth, which while it makes pragmatic sense, it actually doesn't even make pragmatic sense, but assuming under a uniprocessor implementation that it makes some pragmatic sense, it's really belaboring a point. It would be simpler to actually look upon this, replace all those 3 rules by a single rule of this form. So this says that if E1 sigma goes in 0 or more steps, 0 or more moves to some constant m, and E2 sigma goes in 0 or more steps to some constant n, then E1 equals E2 goes to some truth value depending upon essentially this condition, depending upon whether the 2 constants m and n are the same or different, right. So this way you provide an abstraction from the expression transition system, and also another important thing is that by giving a rule of this form you have clearly abstracted away from the order of evaluation of expressions. This rule says that in order to be able to conclude something you require 2 premises, and it really doesn't matter in what order these 2 premises are proved. If you can somehow prove that E1 sigma goes to this constant m sigma and E2 sigma goes to this constant n sigma, then and it doesn't matter in what order, whether you evaluate in parallel, whether you evaluate non-deterministically, whether you partially evaluate one and then partially evaluate the other, it doesn't matter. In some order you evaluate them, and if you get 2 constants, then then this equality of these 2 expressions moves to some truth value. in a single step. Whereas an application of B6 to B8 says that the equality of expressions really has to move in several steps based on the depth of this expression, based on the depth of the Boolean expression E1 equals E2, right. And what it does is that it makes no difference in the abstraction level between the Boolean expressions and the expressions. And even for a simple language, it's actually tedious to go around doing this. If you're going to do things in a recursive descent fashion, it makes sense to do an abstraction at an appropriate level and leave that abstraction as a base case of a lower transition system. And so B9 is actually what you might say an abstraction from the underlying transition system. It also does not specify any order of evaluation, and it greatly simplifies the number of rules that you require, which is important. If such a simple language requires so many rules, then you can imagine what a real programming language would actually look like. Right. So we'll use this abstraction to define the semantics of commands. So we'll assume the existence of the underlying Boolean expression transition system and the integer expression transition system, and look upon commands as some high level entity in which, see, the whole point is that in this kind of an abstraction, what we are saying is, as far as the Boolean expression evaluation is concerned, how many ever steps the sequential expression evaluation might take, all of that is regarded as a single step, one single step in the Boolean expression evaluation, right. And similarly, in the case of the command language, we will look upon as many transitions of the Boolean expression evaluation and the integer expression evaluation steps as constituting a single atomic step of this level, right. Okay, so what about the set of configurations? The set of configurations is just the set of commands. As usual, I'll use this script C to denote the set of all possible commands, small c to denote the syntax tree of commands, of a command, of an arbitrary command. And here we have a slight difference in the sense that once you have executed a program, there is really nothing more to execute. So there is no command at the end of the execution. Once the program execution has terminated, there is no command left. There is nothing to, what is left is only a state, right. So your terminal configurations here are just the collection of possible states. So at the end of a program, at the end of executing a program, all you have is a single state, which is you can look at all the variable value bindings. That's it. There's nothing else left. In the intermediate stages, of course, you have some commands left. So let's look at. So you can see that our command language has two distinct types of entities for the intermediate configurations and the final configuration. Okay, so the assignment statement, all that it says is that the assignment statement can go in a single step to this, to an updated state, provided this expression on the right hand side of the assignment can go in 0 or more steps of the expression language to a constant m. Yeah, and that's in this setting, that's all that is the meaning of the assignment statement. It's you will see that it actually has some far-reaching consequences. Right. So let's look at the rest of the. So the assignment statement constitutes the basis of the command language, right? And That this rule C1 actually is the basis step, right? And now we have to consider compound statements. So, well, the sequential composition that we have got, just like we have a sequential composition of declarations, we could have a sequential composition of commands. And so what does it mean? The sequential composition just says that, let's look at this, let's look at C3 first. If C1 can directly go in a single step, in C1 in a state sigma directly yields you a new state sigma prime with nothing in it, then C1 semicolon C2 in the state sigma yields an intermediate configuration of the form C2 sigma prime, right? Here is where the first state changes actually take place. So this you can look upon as a basis for the sequential composition. So if you have a whole lot of sequential compositions, this C3 tells you that if essentially that if C1 is an atomic command, that means it's an assignment command. In this language, the only atomic command in the command language is the assignment statement. So if C1 is an atomic command which just yields a state change, then this sequential composition gives you this intermediate change. So, and C2 tells you the induction step for the induction on the number of semicolons that are there in a command, right? So this is the basis of the induction over the number of semicolons, right? So if C1 is not an atomic command but is instead itself some complex command, then there is no reason to suspect that in a single step it will give you just a state, it will actually give you some other command. Again, remember that it's all symbol manipulation, so it should give you some other command with possibly a modified state sigma prime. Then then this entire program C1 semicolon C2 then moves in a single step to this configuration with the modified state, right? Okay, so let's look at so this is as far as sequential composition is concerned. C2 is also applicable when C1 is something other than a sequential composition. For example, C1 could be a conditional statement or a looping construct. So in the case of a conditional statement, we will assume that the Boolean can be evaluated in several steps possibly of the Boolean expression transition system to a single truth value. And if that truth value is t, then the effect of this conditional is just to get rid of C2 and everything else and only retain C1 as part of the configuration. Since our Boolean expression transition system did not allow for changes in state, the state remains the same. So this C4 just specifies a transfer of control on evaluating a Boolean expression. That's it. Nothing else happens. I mean, nothing else happens to the program state. There is just a transfer of control that occurs, and the control is such that C2 is discarded after consuming B and getting a truth value t, and this is the program that you have to execute, right? So similarly, of course, if the Boolean condition evaluates in 0 or more steps, this 0 or more steps is important because this Boolean expression, if for example in our language this would not be 0 or more steps, it would be 1 or more steps. But if you actually had if your T and F were actually part of your language, then there is no evaluation involved in this, so it could be 0 or more steps, right? But since my T and F are not part of the language, this will actually turn out to be 1 or more steps, right? So if if the condition B evaluates to false excuse me, then you just discard this branch C1 and you have C2 left. And of course there are no state changes because the evaluation of the Boolean condition does not change the state, and this also just signifies a transfer of control to C2, right. And the while statement is very simple. If the condition B evaluates to true, then you manipulate this while B do C, and there is no state change. What is the, how is the control changed? You execute the body C and then you execute the while statement again. Okay, so what happens is that having evaluated B and having got a truth value T, the program that you have now left to execute is more complex than the program you started out with, because you have to execute the body C and execute while B do C again, right. So in the case of a looping construct, this is how you specify in advance what the transfer of control is going to be. You first transfer control to C and then you append this entire construct again to the end. You sequentially compose this entire construct with the body C, right. Okay, and of course if B is false, then this entire construct works out to a no operation and you get just a state sigma, right. So this denotes the termination condition for the while loop. Right. So this is a since while loops and most imperative constructs are familiar to everybody, I decided to go through it very fast, and anyway it gets too boring otherwise. What we have done is that we have, for Boolean expressions, we have specified complete evaluations. You could actually modify this transition system for partial evaluations. By partial evaluations I mean short circuit evaluations, and you could even do parallel evaluation of Boolean expressions, and you could modify all these transition systems also for parallel evaluation. Okay, I will stop here. This provides a brief overview of both how to specify commands and Boolean expressions. We will get into the more complex issue of stores in the next lecture, and why we require stores and why we require some modeling of memory.